Hey guys, welcome back. Believe it or not, this is only lesson 2. This video is about graphing some of the power functions. So I wrote, given the following functions, f of x equals x squared, g of x equals x to the third, h of x equals x to the fourth, and k of x equals x to the fifth, let's answer some of the following questions. 1. Why do you think I refer to these functions as f, g, h, and k rather than just y equals? You can pause the video, think about the answer, and then hit the play button. I basically refer to them as f, g, h, and k rather than just y's because basically I'm gonna be confused if I just keep writing y equals, y equals, y equals, okay? So that makes it much easier to identify which function you are referring to. I wrote, make a rough sketch of the 4 functions. So here, I'm going to start with f of x, and I'll even put equals y equals x squared. Well, I mentioned this many times. Anytime you want a rough sketch, just pick some numbers. We should know that x squared is a parabola. Okay, so we're going to do what happens at 0, you get 0. What happens when you plug in 1, you get 1. What happens when you plug in 2, you get 2. You get 4. What happens when you plug in negative 1, you get 1. And negative 2, you also get 4. And we basically just get this beautiful parabola. Okay? So anytime you want to, you can always figure out what a graph looks like. That should be g of x. What a graph looks like by just picking some points. So what happens at 0 here for g of x? G of x being x to the third power. 0 to the third is 0. What about 1? 1 to the third is 1. What about negative 1? Negative 1 to the third is negative 1. What about 2? 2 is going to give us 8, so that's all the way up here. What about negative 2? Negative 2 to the third power is negative 8. That's going to be all the way down here. Okay? So what we're going to do is we're going to do this and then this way. It's almost like a chair. So this is what x to the third power looks like. We're now going to do FGH of x is x to the fourth. Now, let's see what happens here. We're going to put 0. 0 to the fourth power is 0. 1 and negative 1. 1 to the fourth is 1. Negative 1 to the fourth is also 1. Now, 2 to the fourth is 16. So that's going to be all the way up here, and that's going to be all the way up here. And what happens now is you get this here. Okay? And we'll talk about the graph later. And here's our k of x being x to the fifth. Well, when you put 0, you get 0. When you put 1, you get 1. When you put negative 1 into x to the fifth, you get negative 1. When you put 2, guys, you get 32. You're all the way up here. And when you put negative 2, you get negative 32. Negative 32. You're all the way down here. I just don't want to cut through this. Okay? So, I'm actually going to flip around a few, let's discuss, I guess. Discuss the symmetry of each group. Is f of x symmetric with respect to the x-axis, y-axis, origin? But I'm going to do it for all of them because I see number 10 says repeat for all of them. So I'm just going to talk about them right now. Y equals x squared, or f of x equals x squared, is symmetrical with the y-axis. It flips nicely over. You should know from the last video, or a few videos behind, that this is an even function because it's symmetrical with the y-axis, and also you can tell because the exponent is even. Okay? This here, y equals, or g of x equals x to the third, it's symmetrical with the origin. It's an odd function. It flips, this part flips here. We also know it's odd because the odd exponent. X to the fourth is symmetrical with the y-axis, and therefore it's going to be an even function, which also has an even degree, by the way. Even, and this is odd. X to the fifth is an odd function, so it's symmetrical with respect to the origin, okay? Show algebraically that they're even or odd, or neither. Well, we already discussed that neither was not an option. So let's show algebraically that they're even or odd. Let's start with this person here. Do you remember how to figure out even and odd? We're going to substitute a negative x. What is a negative squared? Positive. X squared is just x squared. Therefore, if f of x equals f of negative x, it's even. Okay? Let's pick a different color. Same exact thing. Let's show this is odd. We know this is odd because that's a odd exponent. I don't know why I put f. I'm going to put g here. G of x is equal to, pardon me, you're going to put negative x to the third power. What's negative to the third power? That's negative x to the third. So I get exactly my function with the negation, and anytime we have g of negative x equal to the negation of the function, it's odd. Okay, do you remember how to show it algebraically? E, F, G, H. This is supposed to be H, and this is going to be K. Let's put a negative. Negative to an even power is positive, and that's x to the fourth. Therefore, since h of x, which is the original problem, is equal to h of negative x, or vice versa, then it's even, because we got back the same. And here, we're going to show this is odd by, again, putting in a negative x. Okay, and so we have k of x is equal to k of negative x. I'm sorry, negative k of x is equal to k of negative x, so this is odd, right? It's the function, but the opposite sign. So that's how you show it's odd. We get back the same function when we plug in negative x, so therefore it's even. Which graphs are similar? Well, the two even graphs are similar, aren't they? This graph and this graph are similar. The only difference between these two graphs is that x to the fourth, we say stretches vertically. In other words, when you put a 2 into x squared, your y value is just 4. So let me go here. Your y value is just 4. But when you put a 2 into here, your y value is 16. So it basically shoots up really quickly. But these two are similar. And then the odd ones are similar. We're going to learn that these are what we call parent graphs, okay? So we're going to talk about translation soon. But right now, the odds are similar and the evens are similar. And if you're asking, well, does x to the 6 going to follow this? Yes, but it's going to, the only difference with x to the 6 is going to be, let me just do this for you here. X to the 6 is going to be really stretched vertically. So x to the second looks like this. And then x to the fourth is going to look like this. And then x to the 6. And the higher the power, the closer you are going to be, because it's going to be shooting up quickly, okay? But they're all going to actually meet at 1, 1. Anyway, that's just something fun. Discuss the end behavior for each graph. Well, take a look at it. These two are pointing up. These are pointing opposite. We said this before in the previous video. So let me clear this. As x approaches infinity, y approaches, and as x approaches negative infinity, y approaches. Well, if you put a really big positive number in here and you square it, wouldn't you get back a positive? And if you put a really big negative number in here and square it, wouldn't you get back a positive? So therefore, if you take a look at the picture, it should match. On the right side of the graph, or positive infinity, this graph goes up. On the left side of the graph, or negative infinity, this side goes up as well. Well, what about x to the third? Well, as x approaches infinity and x approaches negative infinity, let's see what happens to y. When you put a big positive number, let's get a different color. When we put a big positive number in here and we cube it, don't we get a positive number? And when you put a big negative number in here and you cube it, don't you get a negative number? A negative times a negative times a negative is a negative. So therefore, my end behavior says when x approaches infinity, so does my y. And as x approaches negative infinity, my y does as well. And then we figured out what the drawing looks like, but this is it right here. And basically, the end behaviors are figured out the same exact way for the fifth power and the fourth power. Here's a great question. What is the range for each function? The range is the set of y values. Take a look. Let's do this right here. This one here, the parabola. I'll draw it here for you guys. This is the parabola. Y equals x squared. What is the range? What are the y values? Well, I'm going to do it in interval notation. The range is from 0 to infinity. We're going to include the 0 because it includes 0. Infinity is not a number. Okay, what is the range for x to the third? Well, in this case, you get all the y's down here. And see how the graph is all going up and down? So therefore, your range is from negative infinity to positive infinity. So this is f of x equals x squared, and this is g of x equals x to the third. Similarly, guys, so does x to the fourth and x to the fifth. They both have the same range, okay? What the domain of each function is from negative infinity to infinity. Explain why. Well, we've discussed this many times. These are polynomial functions, right? And we said polynomial functions are continuous functions, which means that you could never insert a number that doesn't give you a y. So every single x value works. So therefore, the domain, which are the x values, they all work. Okay, here's the really great question. On what interval is f of x increasing and or decreasing, if any? And is there a maximum or a minimum point? If so, write the point. And on what interval is the function concave up or down? And find the point of inflection. So there's a lot of terms here. So let's start with the parabola. Y equals x squared. We're going to say that it increases from, we're going to do open bracket, open, from 0 to infinity. That's this part right here. Let me get purple. It's increasing, it's going up, and it's decreasing from negative infinity to 0. Okay? So where is the minimum point? There's no maximum point, but there's a minimum. And I want it as a point, which means I need an x comma y. Isn't it true this is the bottom? So the trick is, when you switch from decreasing to increasing, think about it. When you go from down, decreasing to increasing, don't I hit a minimum? Of course I do. Okay, this is concaved up. Concaved up means that you're looking for a U. That's concaved up. So up like a U. Therefore, it's concaved up from the interval negative infinity to positive infinity, the whole thing. So once it's concaved up, there's no point of inflection. A point of inflection is when you switch concavity. Actually, this and x to the fourth, because they're just the same picture, except for x to the fourth speeds up quicker, is exactly the same. And here's my last part to this video. X to the third and x to the fifth look like this. Okay? So, where is the function, if any, increasing, and where is it decreasing? Well, we know it's not coming down anywhere, right? Here's your function. Follow the arrows. It keeps going up and up and up. So, therefore, from negative infinity to positive infinity, it just keeps increasing and increasing and increasing. So therefore, there's no place where it's decreasing. Now, where is it concaved up and down? Well, can you guys see kind of like a happy face somewhere? Sure. It's right here. See that? So this is concaved up because it's half a happy face. This is concaved up from 0 to infinity. And this is concave down, which is a sad face. Concave down from negative infinity to 0. Wherever it switches concavity, that's your point of inflection. So because there's switches at 0, 0, that's your point of inflection. Point of inflection. And so that's how you do all those problems, okay? I hope this was helpful, and have a great day.